All right. You have now completed your star death region image, and this video focuses on interpreting it physically. In a previous video, we talked about the artistry. The star death regions are mostly about the narrowband emission, also dust emission in the infrared, but in the optical, it's about the narrowband, the O3, the H alpha, the S2. And we learned that you don't have to use natural colors. Here you see a natural color palette where the S2 is red, the H alpha is bomber color, the O3 is a green-blue color. But we learned previously you have all sorts of different color combination, artistic options available to you. But now we're going to focus on the physics and understanding what's going on physically. So I'm going to use as an example the Helix Nebula. This is one that I imaged a year ago. I imaged another one this year. I just haven't processed it yet. So here's my initial optical image. This is my LRGB focused on the stars. It's a planetary nebula. You may notice that the central star is blue compared to the surrounding stars. That's because that's the white dwarf. That's what's left when the star dies and throws off its outer layers, ejects its outer layers. And that star is hot, so it heats that gas, and we see it here. These are natural colors because this is just the LRGB. So you see the bomber color of the hydrogen gas. You see that greenish blue color of the oxygen. Unfortunately, with this one, I didn't get any S2. Okay. And so the first thing you often will do with these star death regions, as you saw previously, is you tamp down the luminance layer, really dim down those stars because we're more interested in the gas. Now, of course, that makes the gas very faint, but I also have hydrogen and oxygen layers that I can now add on top. So it gets brilliant again, and we see the oxygen and the hydrogen. And this is a natural color palette. I tried different things. Here's one where I took the hydrogen and made it red. And I did that because I thought it looked good once I added in the dust layers. And these dust layers come from, well, the orangish one, the heat map, comes from Spitzer, and it has tremendous detail. You see these tendrils, these fingers. We'll talk more about that in just a moment. And in the center, that blue region, that's cooler dust. And I actually took that from Weiss. I liked it better than the Spitzer data. And so what can we learn about this physically? We can learn temperatures and we can learn densities. So here's a table. It's in the module. We have the gas up here, glows at high temperatures. The dust down here glows at lower temperatures. O3 stands out. It's got to be pretty hot to see the O3, from 15,000 Kelvin to about 40,000 Kelvin. If it's hotter than that, the O3 ionizes into O4 and we don't see it anymore. Lower than that, you get O2 and you don't see the O3. So there's a temperature range where you're in the right ionization state. Okay. Beneath that, we see H alpha and S2. They both emit over similar temperature ranges. H alpha from about 5K to 10K. By that, I mean 5,000 to 10,000 Kelvin. S2 emits over a slightly higher temperature range, 8,000 to 15,000 Kelvin. So you might often expect to see it between the oxygen and the hydrogen, but quite often you'll see it on the outside. Even though it's sensitive to higher temperatures, it turns out that this S2 is also sensitive to higher densities. You often have higher densities on the outside. So let's just start with the oxygen and the hydrogen, since that's all I got in this particular image. Again, oxygen 15 to 40,000, hydrogen 5 to 10. And so here we go. We see it's hotter in the middle, cooler in the outskirts, and that makes sense. The source of heat is that white dwarf, high energy light coming off of it, so it heats the inner region more. The outer region, the light is diluted, it's heated less. Okay. Now let's consider the S2. Again, it emits over a similar temperature range as the hydrogen, but it's much more sensitive to density. Higher density, you get more of it. Now this is not a star death region, this is a star forming region, but I include it here because it really illustrates the temperature variation across this region. In the middle here, where you have the stars driving the star forming region, you don't see anything. That means it's probably hot in there, possibly too hot for even the O3 emission. There are other possible explanations. It could be dense in there, and the oxygen can run into itself and de-excite, etc. But the simplest interpretation is it's too hot in here for the O3 emission, and then you have a region of O3 emission, and then you get out here to the hydrogen and sulfur emission. And this is a Hubble palette. So the O3 is blue, the hydrogen is green, and the sulfur is red. And we notice the red on the outside. We don't notice a lot of green because when it combines with the other colors, it comes out kind of yellow. But again, the sulfur is more sensitive to higher temperatures. So what's it doing farther away from the heat source? It's because the density in these star forming regions, the stars turn on, they heat the gas expands, so it's low density in the middle, higher density in the outskirts. That's the cloud from which this all formed. So you'll often see the sulfur farther out than the hydrogen. Now, unfortunately, as I said, I didn't have sulfur for this image, but we can see another density effect from the dust. This is just a single star, but before it died, it blew off layers and layers of gas, and they kind of accumulate. So it's a similar story, lower density, often on the inside with a higher density region farther out. And that higher density region will cool, and when it cools, it forms dust, and we see all this exciting dust in here. And I mentioned these finger-like structures before, and this is what you get when you have low density hot gas, all this stuff, pushing out, running into that higher density cool gas. You get these little tendrils as the hot gas works its way around little dense nodules. And so you get these fingers pushing back towards the direction of the flow of the gas. Again, let me bring up a temperature map, whether you're using Spitzer 8 or Weiss 12, that's about 300 Kelvin dust. And then beyond that, you will often find even colder dust. Spitzer 24, Weiss 22, that's about 100 Kelvin dust. Now, every region has its own story, its own peculiarities. What I find nifty about this one is the blue here, that's the cold dust, and it's not farther out, it's right there in the middle. That's not where you would expect it to be. I was surprised. I had to do some internet searching. You'll need to do some internet searching on your object, particularly for things that are not easily explained. So it turns out the most natural explanation here is as the planetary nebula was expanding, the star, it was a star just like our sun, probably had a solar system. And here you see a solar system and the Kuiper belt where Pluto lives. But out beyond that, we have the field of comets, small bodies, mostly ice. We call ours the Oort cloud. And probably what happened is as that planetary nebula expanded, it broke up, chopped up those small icy bodies, leaving a field of very cold stuff. And that's probably why we have this 100 Kelvin glow here. That's probably a chopped up Oort cloud. So again, Each target is different. It has a unique story and has a physical story. And by looking at the colors and where they are, you can piece it together. All right, I'll stop there.